Hello. This is Introduction to High Performance Computing. I'm Darcy Caleul. I work for the McGill Center for Integrative Neuroscience. Um, yeah, but I'm also, I guess part of why I'm doing this is I'm also in part-time seconded to Caleul, Québec. More on that later. Yeah, but first, a lot of the stuff that I'm going to talk about would certainly not be possible without all the partners that we have, and especially all of the universities that all of this activity is housed at. So please take a look at them. And I'll have a little bit more, I think, to say about Risk and Canary right at the end. Yeah. So, what do we understand by high performance computing? Um, well, it encompasses a lot of areas, and a lot of scientific domains use um, high performance computing. Um, Here's a grab bag of them. Genomics, of course. Genomics deals with large amounts of data and has a lot of processing to do on that genomic data. Molecular dynamics, so chemistry, anything to do with drug design and drug discovery uses a lot of molecular dynamics. And finite element analysis. So what about our brain bucket? That's best described and best modeled with finite element analysis. Computational fluid dynamics, well, that is if we care about sewers and if we care about blood vessels, we use computational fluid dynamics. Now, astronomy and astrophysics, it's just there because it's fun. It's one of the things that is supported highly and well supported by high performance computing, but may not be as related to quantitative life sciences as the others that I'm talking about. Geospatial data analysis is really fun, really interesting too. We've come a long way from just having John Snow thinking of mapping water wells or water pumps in 19th century London. Was it 18th century? 19th century London, because there was a cholera outbreak. A lot of the context of life sciences has spatial and temporal aspects to it. So geospatial data analysis, cool. Visualization and image analysis, wow, that certainly is interesting and really looks good. And in fact, looks so cool and it's so interesting that every year there is a competition for the best visualization using HPC resources here in Canada. So look into that if you've got any cool and interesting visualizations. And here by visualizations, I'm meaning, I'm saying something that needs HPC resources, not just stuff that you can do on your local machine, like regular medical imaging, something that requires a large amount of data and a large amount of, although on your a lot of medical imaging is a very large amount of data too, but something that can't be done right now on your desktop or your laptop. Artificial intelligence and deep learning, I think there'll be another talk about that, so I won't talk about that at all. Humanities and social sciences are an increasing and great area for just the context. I mean, especially in life sciences, it just gives you the epidemiological context within which to work. So if you've got census data can be huge and intimidating, but can give you some good context for comorbidities, etc., etc. You know what I'm talking about. Now, what is HPC? Sometimes you're going to hear, and especially you're going to hear in the Canadian context, people are going to say things like advanced research computing, ARC, as opposed to HPC. In a way, HPC is contained within ARC, but don't mind if you hear either one, high performance computing or advanced research computing, ARC. They're synonymous-y, let's say about that. They overlap. What does that entail? Well, for us at least, it entails large parallel and cluster computing resources. It entails research data management, and that's data management of large data sets in general. It can also be small data sets, but really when we're thinking about research data management within this context, we're thinking of gigabytes to petabytes, right? On that scale. Cloud computing, I'll have a little bit to say later on. Project grid portals too. Just a little thing about project grid portals is how do you want to present the data? How do you want to present those visualizations that you may have, or tools that are attendant to the project that you're doing. Again, a couple more. I'll have a couple more things to say about that. So I've gotten into this a little bit, but let's enumerate it. What is the difference between what you've got on your desktop or on your laptop and what's in an HPC resource, and particularly what's in a node in one of those HPC resources, one of those HPC clusters? Okay. Usually you've got one processor with 2 or 4 cores in your local laptop. On an HPC node, the number of cores and number of processors within the node goes up. Number of cores certainly goes up quite a bit. Processors, though, is usually down to 2 or 4 within one node. You really don't get a ton of processors. Where the scaling is usually is on the number of cores, and those are processing cores that can do arithmetic, etc., within the processor. So this may change, right? So this is current as of 2019, 2020, 2021. Right now, it is usual for laptops and desktops to have 2 to 4 cores per processor. The way things are going, that will change. Okay, that will be up to 8, 16 core, maybe even 32 core per processor. That's how things are going to see. It seems, at least, that's how things are going to scale on the desktop and on the laptop. And there's no reason to think that's not what's going to happen in compute nodes too. I've heard of 256 cores that they're thinking of on compute nodes. Right. So also the RAM that's available. Usually that's pretty constrained by everything that's in your laptop and desktop, unless you're in a really pro machine. Unless you've got a really pro machine, you're not going to be able to add more than 32 gigs RAM. With an HPC node, we want to max that out. We want to get like up to terabytes of RAM in there. As far as storage, as local storage, on your desktop or laptop, I've certainly noticed in the last couple of years, things, because of the transition from hard disks to SSDs to fast SSDs, In fact, it's been going back. I used to be able to easily get, or at least for a good price, get 1 terabyte of hard drive HD storage in my laptop. Now, unfortunately, with my new one, I've got 128 gigs. But that's kind of offset because I use cloud computing for cloud storage. Okay, but because of SSDs, things are pricier, and we've gone back a little bit. With HPC compute nodes, try to go forward. And we try to go forward in a couple of ways, and I'll show this a little later on, is that there's local and there's cluster-wide storage. The cluster-wide storage can get very large. So network cluster storage, local storage versus local storage. So networking, you're usually going to use Wi-Fi. You may plug in and use an Ethernet on your laptop or desktop. In a node, an HPC node, you're only ever going to be plugged in somewhere, okay? So it's going to be Ethernet and another network that is faster than Ethernet, that is low latency and high bandwidth, that is there just to interconnect the nodes themselves, the multiple nodes, so that they can talk to each other quickly. Okay. On your laptop, you may have a gaming GPU, graphics processing unit, and it may be pretty beefy if you can get one now. I think it's easier to get one now than it was a couple months ago. I'm not sure. Actually, I haven't priced them recently. But on HPC nodes, we talk about accelerators in general, specialized hardware, additions to the node, and those usually mean really beefy GPUs. And those GPUs are used for machine learning, for visualization, image processing, etc. Yeah. With your laptop or your desktop, you are directly accessing it, right? You do not directly access a compute node on a cluster. You can get access to one of the head nodes. On this a little bit later. But no, you don't have access to that directly, at least. You have access to it through a submission queue. In general, you know what you do with your laptop and your desktop, but in general, HPC compute nodes, they're for jobs that are, or applications that run across multiple nodes that are unattended for long periods of time. But one of the great things about your laptop or desktop is you can develop and test these applications and these pipelines locally. Now, scaled down versions of them, but it's still so much easier to develop and test locally, and then deploy, do some testing and then deploy on HPC nodes that will run for hours, days, maybe weeks unattended, right? That's why it's important to test beforehand and test locally, right? So that you've got that direct access look at what's happening, because you will not, on the HPC compute node, do not have visibility into what's happening. Well, no, let's say you don't have visibility into what's happening. Okay, so let's specifically talk about what's in a compute node. And I've intimated some of this, is that there's probably a couple of processors, probably with multiple cores in the teens. There's memory associated with those processors. There's some local disk. Okay. There may be an accelerator, a GPU. You may hear TPU, you may hear about FPGAs, but really mostly it's GPUs. So some of these nodes, so we can divide them into classes. GPUs that are compute nodes that have GPUs and compute nodes that don't have GPUs. And in fact, one cluster may have a group of non-GPU'd and GPU'd at the same time, and you can submit to either one of those. Another thing that's that I mentioned is these connect to other parts within the cluster via Ethernet, and specifically to other nodes using a more intense interconnect. In this case, I put InfiniBand there, but there's others you may hear about, like OmniPath. It's just a low latency, high speed that's just meant for quick, high speed talking between the nodes in a cluster. Okay. So let's look at the HPC cluster. So there's hundreds, there's thousands of these nodes that I just showed you in a cluster. And there's a few login nodes, a couple of scheduler nodes, a couple of data mover nodes, and a lot, actually, I should have maybe copy pasted that a few more times, a lot of storage. And that storage is usually on a cluster file system available through Ethernet to all of these nodes, right? So as well as there being local hard disk that is fast to get to, there's this storage that is a little bit less fast to get to, but is enormous, is certainly in the terabytes and the petabyte range, okay? How do we get things into and out of that storage? Well, we have special data mover nodes to get data from other data management systems and other HPC clusters to and from them, and a little bit more on that later. So the only way we can access this HPC cluster is through the login nodes. In general, is through these login nodes. We get assigned to one of these login nodes, or through the data mover nodes where it's open for data movement, data transfer. This we log into, and I'll get into a little bit of that. I think you've had another session on bash shell, usually through command line, through the bash shell, through shells, through a remote shell to these logins. From there, we submit jobs to the scheduler. The scheduler then manages talking to all these nodes, okay? We don't directly talk to all, in general, we don't talk to all of these nodes. We let the scheduler talk to it. And in general, we don't move data directly to them. They're available on the storage that is available to all of them. And that's available in the storage because of the data mover. Okay, we connect usually through these login nodes. These login nodes, we talk to the scheduler. The scheduler talks to the nodes. The data is available to the nodes because we've moved it with a data mover. So what can you expect when you log in, when you do your remote shell? On the login node, as well as on all those compute nodes, it's some Linux-based system. And in fact, it's not a GUI Linux-based system, it's just a shell that you're going to get. So everything is by the command line. At least that way, everything's through the command line. So how do you connect? Well, on Windows now there's WSL, a subsystem for Linux, and there's a terminal app now. I suggest getting familiar with those. Mac OS has always had a terminal app. That's what I use. In fact, it has prominence in my doc, is that terminal app. And within the terminal, you can use a couple commands, SSH and SCP, but there are also GUIs that allow you to do transfers, simple transfers, local transfers for your machine to a login machine, like CyberDuck, WinSCP. Just there's a ton of GUI tools to do that if you don't want to do those transfers on the thing on the command line. And by transfers, I do mean small ones that you'll attend. This isn't for the large terabyte to petabyte range data. This is small input, small amounts of code, up to a gigabyte, let's say, up to gigabytes in size. So I just want to highlight this again. To develop stuff, you're really, and to work with on those login nodes, well, to get stuff done on those login nodes, to be able to submit work to the compute nodes, you're really going to get used to the command line. Okay. And we're going to talk about software and scientific software and libraries a bit later. A bit later, or is it next? A bit later. And you should certainly use version control software. Now, alleviating this somewhat is there may be web portals that provide certain interfaces, certain nice interfaces to that data, or to those visualizations, or to that a way to look at or start these processes. Those are general third-party things. We're not going to get into. Other than, here we go with transferring. One of the ways that you can transfer very large data is with Globus. And Globus is a web interface. It's one of these third-party web interfaces that will allow you to move from one cluster to another, or from one large data management center to a cluster, terabytes and petabytes of information. And what it does is it does this. You start it, you say, I want this done, and it will come back and notify you later when that transfer is done. So it's unattended, and it's third party. So that's really important, is that when you tell this Globus web portal to do this transfer, it tells those two endpoints, the originating and the target, to do it between themselves. It's not coming through Globus. It's not coming through your machine to go to somewhere else. It is in fact being transferred from one directly to the other. That's a good thing. And I think I will mention why in a bit. So that's a little bit of a tease. Okay, we have in that environment, in those cluster environments, we have a lot of different scientific software and scientific libraries for you to use. And those are managed through a module system, through this module system that we call LMOD. And as well as some compilers, there's lots of interpreters. You may have some Python, some R experience. And common libraries, high-performance libraries to use are OpenMPI, Boost, OpenBlast. If you don't know about it, that's fine. That's a whole nother topic. But certainly tools, command line tools that you can use right now, FreeServer, FSL, etc. A lot of good stuff. And you can always ask for software to be added to that module system. And the reason we do that, and we ask you to do that, rather than compiling some of these high performance applications and pipelines yourself, which you should do for your own custom code, certainly. But why we do that for some of these big third-party tools is that these are all tuned for these node architectures when it's in the module system. These are recompiled and they're made sure to work well with the specific HPC nodes. Okay, but any of your glue stuff that you've written in Python or R that use these libraries and that use these tools themselves, these third-party tools, that you should very much be developing on your workstation, your laptop, and then moving over to the HPC cluster and using it that way, or yeah, doing it that way. So I mentioned this thing about jobs. So everything on a cluster, if you remember the cluster diagram, is everything on the cluster for those compute nodes. Everything, almost everything, 99%, is there because of a scheduling system, because it goes through a scheduling system. And sometimes you'll hear batch system, batch as opposed to immediate or generic, or as opposed to your desktop or your laptop. And in general, we use that because the login nodes are just for that. They're just for login and then talking to the schedulers. And it's the scheduler's job to make sure that what you've told them to do with the compute nodes happens, and happens over, again, hours, days, weeks, months, sometimes months. Yeah, let's go to weeks, but sometimes months. And it's checking in on them, and it's making sure that everything's running fine, and it's making sure to restart certain things that aren't working. Sometimes that's another aspect, and that's another aspect to get into the software development part of how you develop a pipeline to work on a cluster. Okay, but one of the great things about this scheduler is it uses a fair share policy, and tweaked a little bit, but that's an area that I'll get to Compute Canada in a bit, but is really looked into a lot about what makes sense for individuals. How do individuals, when they submit a job, what is fair to them? Not only what is fair to them, but they're part of a group. What is fair to the group that they're a part of? And how is it fair to other groups that are using the scheduling system and other users within those groups actually accessing those nodes? There's no good answer, but there's policies, and we can communicate those policies and talk about those policies about what fair share means in the scheduling context. Cloud systems, I'll just have a few things to say about this, but where HPC nodes are kind of set in stone by the provider, by the HPC cluster provider, what their operating system is, what modules are available on them, how you can access them, that is through a scheduling system. Clouds are kind of the opposite. You may have heard of IaaS, Infrastructure as a Service. And at least this is what it means to me, is that you can allocate virtual machines networks that tie together these virtual machines and storage, and well, networks that tie together the storage and the virtual machines on the fly. You can do this lickety split. Well, by lickety split, I mean this isn't milliseconds. This is seconds and minutes sometimes for these VMs to come up. But certainly faster than you can do something with than you can schedule your job for an HPC cluster. Now, another difference between this is the VMs that you get, these virtual machines that you get up, they look like a machine. They may kind of look internally like a machine, one of the nodes, but they're blank slates for you. You can install whatever OS you want on them, and even Windows, but you have to come with the Windows licenses. We don't really have, when I say we here, I mean Compute Canada, don't really have licenses for running Windows or Mac OS inside these VMs. So you're still very much, yes, very much constrained to some Linux variant. But at least it's some Linux variant that you may be more, or BSD variant that you may be more accustomed to. Not only the OS, but the libraries and the software, completely up to you what you install in those. It's completely managed by you. That can be useful for a lot of non-standard things. But let me give you an example what it can be used for that nodes and login nodes in HPC clusters can. You can start up a web server in these and put up a project-oriented portal that does specific things with the data that you've that you've run through the HPC node, or I don't have a great example, but you can think of this is where you come in. You think of a web portal that'll offer a specific service with the results of the HPC work that you've done. So, what's my timing like? I am over 30 minutes in, so perfect. Let's talk specifically about what's available to you in the Canadian and Quebec context, and McGill certainly context. Right now in the Canadian context, there's Compute Canada, and it has a certain niche within this overall tree structure, and it offers advanced research computing, to some extent some research software support. All of these internal nodes will change, certainly within the next couple of years. There will be a realignment, there will be a reimagining of who does what and what directorates will do what. Enough said. But these 4-leaf nodes will always be there for the foreseeable future, will always be something that will be delivered by whatever this internal mess is like. Well, it's not a mess, but these internal institutions, okay? There will always be a digital network for research and education. And here I talked about RISC and Canary. RISC is the Quebec réseau pour whatever IS is, réseau pour informatique scientifique. I'm not sure, I don't remember. and Canary. And these do a great job of having high-speed, dedicated networks between research institutions, between universities, and all of your research data, in theory, can go over these. And one of the great things about Canary too is it peers with international research and education networks. So if you've got data that you want to access that's in Amsterdam or Geneva, that's at a research institution in the Netherlands or in Switzerland, you can quickly transfer at a really good bandwidth from there to McGill or to an HPC cluster that you have available to you. Okay, that's the important sort of canary in risk, is the data transfer part of this. So the Globus thing that I mentioned before goes over these links. Research data management is a whole nother subject that I wish I could get into, that deserves its own talk, deserves its own set of talks. But what do you do with the data once it's transferred? How do you manage it? How do you curate? How do you add metadata? How do you do this, that, the other thing? How do you get it ready for use by research software and advanced research computing? Research software and research software development and research software integration is always going to be one of those four, I wouldn't say pillars, again, I'd say leaf nodes in there. There's a lot to say there. There's a lot to say about research software development, but developing pipelines. Wish I had a whole other session to talk to you about that. But yeah, so here we're talking about advanced research computing. And you see why I introduced ARC into this is because in the Canadian context, ARC is used a lot more than HPC for some reason, okay? And that's where Compute Canada comes in. Now, Compute Canada is really a consortium of regional partners, which are, each of which are in fact a consortium of research institutions and universities that use it. Just like RISC is kind of a consortium for the networking between those institutions. Québec and Compute Canada is a consortium for common management structures, common software, common just a bunch of stuff that we do with our HPC resources in Canada and in Quebec. And here there are four regional partners. Westgrid, which is the four western provinces, Compute Ontario, Québec, us, yay, and AceNet, which is the four Atlantic provinces. Okay, now I'll mention this a bit later, but all of us offer all of these local regional partners offer a lot of the same services, and we coordinate on what services we're going to offer. Okay. Now, there are about 200 analysts, and this number may be off. This was a 2019 number, that are available, that are spread across Canadian universities, which are the actual members of Westgrid and Compute Ontario and AceNet and by extension Compute Canada. Great things about this is, so we have a lot of experts at Québec. We have a lot of good people, but we may not have an expert that we can refer you to within Caleul, Quebec about, let's say, Julia. Maybe you like Julia, the language, and you like doing stuff in Julia. I know that there are a couple of people in WestGrid that I can refer you to. More on this a little bit later. So, Caleul, Quebec has about 50 people. Again, I think this is 2020, 2019. I do not have the current exact number of how many people we have, but we have so many good people. And they are like me, except most of them are full-time Caleul, Quebec, full-time seconded from their home institutions like Laval or McGill to Caleul, Quebec. I'm just part-time Caleul, Quebec, part-time MSIN. So many good, and they do, well, what I do, user support, they do workshops, they, some people are system administrators. I'm an analyst, I'm an HPC analyst, and I get out there and I help people and develop things for people and do stuff like this. Yeah, and there's so many people out there from UDM, from Laval, not just McGill, that do this. Yeah, there's some internal management, scientific and operational directors, and the big resource that we offer is Beluga. And Beluga High Performance Computing Cluster is housed at ETS, so down in Griffintown. I think you can ask for a tour. You couldn't during COVID. Maybe you can get a tour now. I'm unsure, actually. If anybody really wants to see it, there are obviously pictures online, and I think you can wander on down to ATS and look in the windows. There are windows to see it. That will be changing again within the next 1 or 2 years. We will have another new HPC resource, Narwhal, to work on. So we're always, and in fact, our partners are always looking, once they've built their current cluster, they're always looking at the next one, always. Always to make it better. And here I will tell you why. So right now we have 4 large clusters that are available to you as a Compute Canada, if you have a Compute Canada account. Okay, Niagara out of Toronto, Cedar out of SFU, up the mountain-ish, kind of in Vancouver, wherever SFU is, Graham and Waterloo, and Beluga at McGill, housed at ETS, housed graciously at ETS. All of these are on the top 500 supercomputer list, except I think in the last couple, Graham may have dropped off that list. But I know Beluga, Cedar, and Niagara are still well ensconced in the middle of that list, in the middle to top of that top 500 supercomputers around the world list. So these are great resources that you have access to and that you can use for any high performance computing need you have. Yeah, how do we access that? How do you get access to this? Well, one of the things I told you that Compute Canada does has some common services between Caleul, Quebec and AceNet and Compute Ontario and WestGrid. One of them is CCDB. So if you have a CCDB account, you can use any of these machines. You can log into any of these machines. How do you get an account? Well, a principal investigator has to have requested a role, has to have requested an account. And if you are not a principal investigator, when you go to register or open an account, you have to register with respect to a principal investigator that you're working with. Okay, so anybody that's working with one, so uh, student of any kind, postdoc, research programmer like me, or analyst like me, um, you apply and say what PI you're associated with, and that PI will get the request and say yay or nay. Once you've got an account active, you can connect to any of those four national systems that I just talked about. Now there's a lot. There's not a lot. There's some rules to follow, but that's all in the documentation that will be sent to you once you log in. Okay, I'll give you a little bit of. I'm going to wrap up here and give you a little bit of time, and give you time away from me, my umming and ahhing for just a bit. Please go see things like Compute Canada. Has a lot of information. There's a lot of information about starting up, about who we are, what we do at Compute Canada and Caleul, Quebec. Caleul, Quebec has information too. Go there, look, see. And docs.compute Canada, again, one of those services that we've put into Compute Canada, but that Compute Quebec, Caleul, Quebec, does so much to put into. These docs are a wiki of information about how to use this, how to use that, how to set up to do this, how to set up to do that. There's a ton of information in docs.computecanada.ca, and a ton of information about how to do that specifically on Beluga too, the Caleul Quebec run HPC resource. So please go see that. And in fact, what I just said about registering, about signing up for Caleul Quebec or Compute Canada, is there in those docs too. Okay. Upcoming, one of the things that we do, and one of the things that we do regularly, is these outreach and training opportunities. And you can see that, at least for Caleul Quebec, at caleulquebec.eventbrite.com. We put everything upcoming on that. And I don't think there's anything upcoming right now. But you can get to those remotely, whoever you are. Doesn't matter. Okay? As well as Caleul Quebec, both AceNet and WestGrid, I would go back to that Compute Canada site, both AceNet and WestGrid give excellent training things on some of the stuff that we don't do training on, such as Julia, which I mentioned. Just some really top level training stuff online. Go see them and go see what they have coming up. And of course, they've recorded a lot of the material, and a lot of the material is there. And I believe, yeah, just as a Caleul Quebec, as a Compute Canada member, you can go for training in any one of those regional consortiums, regional WestGrid, AceNet, Compute Canada, etc. Compute Ontario. So please go to check that out. Another thing that Compute Canada offers federally is this support endpoint, support at computecanada.ca. That goes to a ticket system that if you're coming from a Quebec institution, and especially if you're talking si vos questions sont en français, come to us at Calcul Québec. And if there are questions particularly about Beluga, etc., particularly come to us at Calcul Québec. But if it's a general problem about CCDB or about Julia or something that maybe we don't have access to, this is how we get you access to the other people in Compute Canada that may have answers and may be able to lead you through the process. Lots of good people. So if you have questions about registering, if you have questions about Beluga, about accessing Beluga, about something that isn't clear in the docs.computecanada.ca, don't be shy to send us something to support at computecanada.ca. There's somebody always, at least from Calcul Quebec point of view, we have one or two people that are full-time watching well, not that email address, but that email address that goes into a ticket system, and that hands it off to me or to whomever. So don't be shy about support at computecanada.ca. Don't be shy about those docs, that wiki at computecanada.ca. And don't be shy to go see other things that Calcul Québec and Compute Canada gives. And I guess I'm going to end here because we've got 10 minutes left. 10 minutes left. And yeah, okay. Thank you.